we'll start again. So I just want to quickly recall what I did last time. So let's go a little bigger one. So so what we were doing, we were trying to understand. So X was a random variable. On a sample space S and events P, F, and probability P. So and then we decide so X was a discrete random variable as far as we were concerned, and for that we defined expectation of X as the sum over T in T, chance that X takes the value T times the times T, and this we interpreted as this if T is countable. So this only if it converges absolutely, we say E of X is finite. If it diverges to infinity, plus or minus infinity, we say X has infinite expectation. And then if it doesn't do either, if it just diverges somewhere else as a series, then we say that E of X is not defined. That's what we had done last. We sort of stabilized E of X. And then we had shown several properties of E of X. One was that if you have E of X is finite, it's the same as saying that E of the absolute value of X is finite. So this is a very important property of E of X. And it also said that we had shown a particular property of sums of random variables. We had said that E of X plus Y we had shown was equal to E of X plus E of Y. And this is provided, so the caveat here is that provided both E of X and E of Y exist. And it's finite. So that unless sum is not formally defined. We also showed that E of the constant random variable is just the constant. And we hadn't shown this one part, which I will leave as an exercise, is the fact that that E of alpha times X is equal to alpha times E of X for any alpha. Real provided E of X is finite. So this is what we had shown last time, and we proceed from there and go to the next step. So now what we'll do now is that we'll try and understand how far this can go. Like for example, it's linear, so these two facts will imply that E of alpha X plus beta Y is equal to alpha times E of X plus beta times E of Y. So this is just for any alpha, beta, and provided again E of X is finite and E of Y is finite. So this is something that one can easily show. So these two things I will leave as exercises. I will not try and show them in this level. This is where we were last time. So now I'd like to build on this a little bit and understand what E of X actually means for random variable. So understand. So the first thing is you know it sums across as linear. So it's a what happens to products? So let's just see a simple example. Let's say this is example 4.1.11. So the idea is the following: that let's say x is uniform 1, 2, 3, and let's say y is 4 minus x. So now it's easy to verify that. So let's see. So y takes the range of y is again 4 minus 1 is 3. It's again 1, 2, and 3. And it's an easy exercise to check that probability that y equal to I is just 1 over 3 for all I. So y also is uniform 1, 2, 3. So y also is uniform 1, 2, 3. So now if you do E of x, that's just going to be the sum from I equal to 1 to 3, I times the chance that x is equal to I, and that's the same as 1 times 1/3 plus 2 times 1/3, plus 3 times 1/3, and that gives you 3 plus 2 plus 1 is 6 by 3, and that's 2. So since x and y are the same distribution, this will also imply that E of y is also equal to 2. So E of x and E of y is 2. Now, again, we have seen the expectation sums up. So E of x plus y will be E of x times E of plus E of y. But what happens to something like, let's say, if I take z equal to x times y, then what happens? So what is x times y? X times y, range of z is x times y. So you have to take all possible values. So it's 1. It's 1. So 1 into 1 is 1, 1 into 2 is 2, and then 3, and then can be all possible. So multiply everybody is like 4, and 6, and 9. Right? These are the values z can take. No, sorry, it's not right. So I mean x is 4 times. Sorry about that. So x is this is equal to 4x times 4 minus x. Sorry, and that's the same as 4x minus x squared. And so this you can easily check. So if x is 1, this belongs to if x is 1, this belongs to 4 minus 1 is 3. If x is 2, it's 8 minus 4 is x is 2, it's 4 times 2 is 8, minus 4 is just 4. Right? And x is 3, it's 12 minus 9, which is 3 again. So this is all it can take, 3 and 4. Or am I making a mistake again? It's 4 minus 1 is 3. That's 3. Right. So then the chance that z is equal to 3 is the same as the chance that x is equal to 1 or x is equal to 3. So that gives you 1/3 plus 1/3, and that's 2/3. Now the chance that z is equal to 4, that happens only when x is 4, right? And that happens with probability 1/3. So that's a distribution of z. So now this implies the following, that E of z is going to be equal to 1/3. Sorry, E of z is going to be what? Z takes two values, value 3 with probability 2/3, and value 4 with probability 1/3. And that's going to give you 6 plus 4 is 10/3. Okay. So now you observe two things now, that E of Z is what you have shown is that E of XY is Z is going to be 10/3. And that's not the same as let's say E of X times E of Y, because that was both 2. So that means the expectation doesn't sort of suitably generalize in general. That is, in general, it's a very sort of common mistake people make in beginning of probability, that the expectation doesn't automatically go across as a product. This is also obvious for you. If you take two sequences of numbers, you take their means first and multiply them, or you take the product and find the mean, they do not match. That's a very important aspect of this one. Very nice. So now what's the crucial, but this is true in some situations, so I'll write the theorem down. It's kind of a unique idea in probability that it's a simple fact moment you see it, but this thing is not true in general, but it is true in the following situation, that if the random variables are independent, then the thing splits up as a product. No, nice fact. So suppose X and Y are discrete random variables. Both with finite expectations. Value, right? And let's say both defined on the same sample space. That's important. Sample space S. If X and Y are independent, then E of XY is the same as E of X times E of Y. So this is a very important aspect in probability. So the expectation kind of moves across the product only if the random variable is independent, or if random variable. So this equality can also be true otherwise, but in general it's not true like we have seen before. So we just quickly recap what the results are. Let me go to the split view again. So here the idea was the following, that so we had done this thing earlier, that E of X is linear, and we also immediately check that as a product it doesn't sort of go across. That E of XY is not the same as E of X times E of Y, and that's a simple example. And this theorem tells you that if they're independent, then the sum is plus the product. Though I just want to just clarify that it's not an if and only if condition. You could have the equality be true and the random variables not be independent. We will check that as we go along the course. But in general, E of XY is not equal to E of X times E of Y. So now let me sort of get back to this idea of how to prove this theorem. So how does one prove it? The proof is fairly straightforward. You have to independence crucially. Let's do this. Proof is fairly straightforward. So I have X is from, let's say, a sample space S to, let's say, range is T. Let's say Y is from sample space S to, let's say its range is U, then xy would take one. X times y would take values from S to, let's say, a sample space, let's say, let me just change notation a little bit so it's easy for me. Let me call this as U, let me call this as my V, and let's say T, where T is the set over U times V, such that U is in U and V is in V. So now what happens? Now what is E of xy? E of x times y is the same as the sum over x, sum over t in t, t times the chance that x times y is equal to t. That's what random variable xy looks like. And now this is the same as the sum over u and u, v and v. So let me write this in a little different color so it's a little easier. So let's say u and u, and let's say v and v. It's the chance of u times v, and then you'll have x is equal to this and y is equal to this. So I'll write that x equal to u and y and times u here, and I have a v, so v and then x equal to u. That's how I write it. Again, one has to verify that this going this way, you have to be a little careful because a priori we do not know the series converges. But if you write the proof down in the backwards way, it will be clear. So I'll just go through it formally at this step. So next step is what you do is you write this as the sum. So now the u and the v split up in the sense the following way. So here use a crucial fact that is u and u, v and v. So you have v, and then you have a u, and then you here is the fact use the fact that x and y are independent. So if you use that, then you know that this is the same as the chance that x is equal to u times the chance that y is equal to u. Right. That's what you get here. Right? So now you observe that that it's a sum of one term depends only on u, the other term depends only on u, and it splits up as a product of two things. So this, if you think a little bit and make it rigorous, it's the same as the sum over u and sum over v and v. So sum over u and u and sum over and times the chance that x is equal to u and times the chance that y is equal to v. So here you'll have y and u, and here you'll have v and v. Then so it splits up, the sum splits up as a product. And that, if you think about, you just look at it, and there's a u here. That, if you just observe, is just the same as e of x times e of y. So the just to sort of be a little bit careful, one shouldn't go in this order. One should go in reverse order because you only know that e of x and e of y exists. So just a word of caution. If you want to be precise about mathematics, you start with e of x times e of y. E of x times e of y, and work backwards for a precise proof. So you'll use what all you use that you use series converges absolutely. And you use rearrangements are okay, and independence to get to exy. So to do it precisely, you go backwards. You don't go forwards. Though I went forwards because just to sort of give you the idea. But if you were to do the precise proof, you'd start with e of x times e of y, go to this step, and now you know series converges absolutely, so you can do anything you want. You can multiply it like this, up and down. Once you come here, you use independence to show this product is the same as this joint probability. and then you use the fact that the same as this guy, and then you on the other. So that's how you do it precisely. So that's one important aspect of independence. That is the sum. That is the random variables, product random variables. The mean splits up as a product. Very nice. So a couple of things before I sort of move on to other aspects of random variable. Understanding more specific numbers about random variables is the following. So two facts I want to sort of illustrate. One is that is the following. So let's do some standard distributions. Let's say x is geometric p. So how do you compute the mean of x? So let's say what is mean of x? So what's the mean of x going to be if x is geometric? So we already seen that x is uniform. We know how to compute it because it's a finite set. Sum is finite. So geometric. Let me just walk you through the computation. So what does geometric mean? Range of x is 1, 2, 3, and so on and so forth. The distribution of x is what? The probability that x is equal to k is just, you'll have k minus 1 failures, and at the last kth trial, you have success. This is for k and 1, k in the range of x. Any k in the range of x. So now this implies, so what does E of x mean? So E of x traditionally, E of x by definition is just going to be the sum over k equal to 1 to infinity, k times the chance that x is equal to k. Right? That's what it is. So, but we have to make this computation precise, so I'll just do this series computation in a precise way. So how does one do this? So first one defines T sub n as the sum. So what am I going to do? I'm going to compute the series, right? I'm going to compute the series. So what I do is T sub n is the same as k equal to 1 to n, k times the chance that x is equal to k. That's what one would have to compute first to do the geometric. So what's that going to be? That's just going to be the sum from k equal to 1 to n, k times p times 1 minus p to the power k minus 1. Right. So this, again, I do a little trick. I just think of this as the sum from k equal to 1 to n. Make it right here itself. Is the sum from k equal to 1 to n, k times, here I think of this p as 1 minus p. And then this remains the same as 1 minus k minus 1. So all I did was replace this p here by the same quantity, but I wrote it a little differently. But now if I multiply the product out, it's an easy exercise by rearrangement. It's all finite sum, so I can arrange any way I want to arrange. And I have a pseudoscopic sum in some sense. So I'll have k equal to 1 to n, k times 1 minus p to the k minus 1. That's a simple algebra. Right? Simple algebra. Now once you have that, you're on your way, because now this also is a little bit, so this is this, okay, let me just do this. This is this minus the sum from k equal to 1 to n, k times 1 minus p to the power k. So I'm just multiplying it out. So simple algebra gives that. Now what happens to this guy? So now if you notice, it's kind of alternates, right? This is k times 1 to the k minus 1, and then k times 1 minus p to the k. So all you'll be left with is the sum from k equal to 1 to n. For each person, you'll have 1 minus p to the power k minus 1 as the only one left. And then the last person here will be left alone. So it's 1 minus p to the power n and times it. That's what you get here. So So maybe I should just move this simple algebra step to this particular. So now this is easier. The geometric sum, we know how to do this. This is just r to the power k minus 1 from 1 to n. The first term is 1. So it's 1 minus p to the power n minus 1. The whole thing divided by 1 minus p, right? That's what this is. Then minus n times 1 minus p to the power n. So here I'll use the fact that I'll use the geometric series. Now I go to the next step, and then this I do a little algebra. I have a p at the bottom. So I just read this as 1 minus p to the power n minus 1 by p minus n times 1 minus p to the power n. So now here you have to use two analysis facts. So one fact you have to use is that, so the fact of analysis that you have to use, or calculus. Analysis is the following, that limit as n tends to infinity of 1 minus p to the power n minus 1 is equal to 0. That's one fact you need to use. The other fact you need to use is that, should I make a mistake here? There are how many terms here? There are n terms here. Should put an n here. Sorry about that. Here I'll have n again. And you also use the fact that limit as n tends to infinity, n times 1 minus p to the power n is also 0. These two things, I'll assume that these two things are true. Once you have these two things, then what happens is that we see that Tn converges to 1 over p as n goes to infinity. So that means, therefore, the expected value of x, which was the series, so the series right here, we had the series right here, right? This is the series, which has the series. Let's copy this down. The series. So it is the series is equal to this. So let me erase this. Therefore, e of x, which was this particular series that we had, is also equal to 1 over. So as e of x was equal to this, e of x is essentially the limit of Tn's, and that's just 1. This is an important computation. So to do probability properly, one needs to sort of be careful of using calculus results that you just have to make sure whenever you use calculus analysis results, just be precise about it. Even though formally this computation will be easy to do, it requires some jugglery. So there's sort of a way to do all standard distributions. You can do Poisson, you can do in this fashion. So it's simple exercise to try and check Poisson. So you should try and do exercise like this. Let me try and write the exercise down. So here, simple exercise you should try is that if x is Poisson, with lambda you find e of x. So it's another series computation. For all finitely many ones, you can easily do this. It's not hard to do this. So if x is Bernoulli, then you know you can just show that e of x is going to be equal to p. If x is binomial np, n comma p, then you know that e of x is going to be. You can just check that e of x is equal to n times p. There are many ways of doing this. I want to check that and see. One last aspect of expectations of random variables as such as before. So now, like we already seen, if you have a random variable x and you have a function of it, then we know how to compute the distribution. You invert the function and then try to compute the distribution. So similarly, if I have a random variable x, so if we have random variable x, and we have x from, let's say, s to t, and we have function f from, let's say, t to the real line, and let's say x is a discrete random variable, so t is countable, so f only takes countable values. Then you take y equal to f of x, then y also has y also is a discrete random variable. And then now, if I have to find e of y, I want to ask you why. So one method we know is the following. So one method is a method is the following. So you find a range of y, right? And then for each y in y, you do two steps. You do each. So sorry. So one step is you find range of y. That's the first thing. Then you say that for each y in y, you try and find the probability y equal to y. You find for all y in range of y. Right? Then once you have this step, and then you do the following. Then you say, when you compute summation over y and range of y, you do y times the chance that y equal to y, and that will give you the answer of e of y. This is one way of doing this whole thing. But this may be cumbersome because you keep. Let's try and do it kind of cumbersome do this again. You want to keep find distribution of y and then do the whole thing. We just try and see if there's an easier way to do this. So let me try and outline a sort of an idea before I sort of. So the idea is that I have y is f of x, right? So I know e of x. I know e of x is the same as the chance that x is in t. I sum over all possible values in t, e of t. Right? Can I somehow use the distribution of x to find this? Can we use a distribution of x to find e of y? Right? Without going to computing explicitly the distribution of y. So without computing distribution of y. Okay, that's the goal. So the idea is that you know that one way to compute f of x, e of x, to find the distribution of f of x, and then do the definition. What can we do without that? So here's one idea. I'll try and illustrate the idea. And let's see. So here's an idea. So what is let's write the proof down. So what is e of y? So e of y is e of f of x is going to be. So this is an approach. E of f of x is going to be what? Like we discussed, is going to be the sum from, let's say, f is from, let's say the range of f. Let's call it as u. So it's range of u. So it's going to be the sum. I'll rewrite it in the following way: sum over u and u, right? U times the chance that f of x is equal. Right? That's the definition. So of course now I don't know if the things exist or not, but let's assume everything all sums exist and they're all finite. Now I come here. Now observe the following: f of x is equal to u. This event is the same as the set of all. How do I get all sample points for f of x equal to u? What I do is I take the union over all t in t, right? All t in t, such that f of x is equal to t. So such that. So instead of writing it like this, I'll rewrite it a little differently. I just take all t in f inverse of u such that x is equal to u. These are both the same events. X equal to, they are both the same events. So this is a set theoretic exercise that one has to sort of, it's a set theory exercise to establish this fact. That is, f of x equal to u is the same as the union over t in f inverse of u such that x is equal. Now, let's say I use this fact. So I use this fact, let me call it a star. So using star, so what do we have? We have e of f of x is the same as the sum over u and u, that remains the same, right? I have a u. I just replace this probability of f of x equal to u as the probability of the union over t and f inverse of u, x equal to t. Right? I'm not doing anything fancy here, I'm just doing that. But that's a disjoint union, so that means I can write it as the sum over u and u times the sum over t in f inverse of u, probability x equal. Now this implies? This implies a very interesting thing. So I have the sum over u and u and sum over t in f inverse of u. So I can now think of I can flip this sum if you allow me. That's the same as, or I can move the u inside. So I can think of this as the sum over u and u, right? The sum over t and f inverse of u. I can think of u times the chance that x is equal. But what was u? U was f of t. So I can just think of this as the sum over u and u, sum over t and f inverse of u, f of t times the chance that x is equal. But sum over u and then sum over t, f inverse of u, that's just one sum. That's just the sum over t and t, f of t times the probability x equal. So this step is just this is the final idea, is that all I have to do is t is just f inverse of u. Right? That's all I'm using. Right? That's all I'm using. So in this step, all I'm using is the fact is that the set t is just f inverse of u. Right? That's all I'm using. So now you see what I've done. I started off with ef of x. I want to know this, but then I came here. Maybe I'll write different colors so it can be a little easier. So that if I remove all the t's, so I have t in f inverse of u, x equal to t. Right? That's how I got this idea. Right? This idea I got here. That is, whenever f of x was u, that came from some number t for which f of t was equal to t. Once I have this, then I'm here again. Then I come here in this step. I replace the step here. I do the fact that these are all mutually exclusive events, so I can just sum the probabilities up. So that's easy to do. Then I come along, then I say, okay, fine. Oh, I can read the sum this way. I can pull the u inside. So I have this t here. I have this t outside. So I have t times x equal to t. Then what I do is observe is that u is the same as f of t. There's no difference under the sum condition, right? So u is same as f of t. So I get f of t here. So I get x equal to t in this. Then once you observe that capital T is same as f inverse of u. There's no difference. So all this is just one sum. It's just the sum over t and t, f of t times chance equal. So what we've achieved in this computation is the following, that I don't need to go and compute f of x equal to u. I can just work with x equal to t to get my answer. So here's the theorem that I've shown in this calculation. So let me write the theorem down. The theorem is the following, that so what we have shown is, we have actually shown this theorem. The theorem is, so this theorem 4.1.19 in my book. So the theorem is the following, that let x be a random variable from S to T, be a discrete random variable, you define a function f from T to U. Then the expected value, 125 is too much. Then the expected value of f of x may be computed as E f of x is the same as the chance of T in T times the probability mass function of x, which is probability x. So there's no need of computing distribution of f to compute the distribution, compute expected value of x. It's just you can use the distribution of x itself to finish the problem.